In mathematics, a polynomial is an expression consisting of variables and coefficients, that involves only the operations of addition, subtraction, multiplication, and non-negative integer exponents. An example of a polynomial of a single indeterminate, x, is x2 minus 4x plus 7, which is a quadratic polynomial. An example in 3 variables is x3 plus 2xyz2 plus yz plus 1. Polynomials appear in a wide variety of areas of mathematics and science. For example, they are used to form polynomial equations, which encode a wide range of problems, from elementary word problems to complicated problems in the sciences. They are used to define polynomial functions, which appear in settings ranging from basic chemistry and physics to economics and social science. They are used in calculus and numerical analysis to approximate other functions. In advanced mathematics, polynomials are used to construct polynomial rings and algebraic varieties. Central concepts in algebra and algebraic geometry. Etymology. According to the Oxford English Dictionary, polynomial succeeded the term binomial, and was made simply by replacing the Latin root bi with the Greek poly, which comes from the Greek word for many. The word polynomial was first used in the 17th century. Notation and terminology. The x occurring in a polynomial is commonly called either a variable or an indeterminate. When the polynomial is considered for itself, x is a fixed symbol which does not have any value. It is thus more correct to call it an indeterminate. However, when one considers the function defined by the polynomial, then x represents the argument of the function, and is therefore called the variable. Many authors use these two words interchangeably, but this may be sometimes confusing and is not done in this article. It is a common convention to use uppercase letters for the indeterminates and the corresponding lowercase letters for the variables of the associated function. It may be confusing that a polynomial p in the indeterminate x may appear in the formulas either as p or as p. Normally, the name of the polynomial is p, not p. However, if it denotes a number, a variable, another polynomial, or, more generally any expression, then p denotes, by convention, the result of substituting x by in p. For example, the polynomial p defines the function in particular. If r equals x, then the definition of p implies this equality allows writing, let p be a polynomial, as a shorthand for, let p be a polynomial in the indeterminate, x. On the other hand, when it is not necessary to emphasize the name of the indeterminate, many formulas are much simpler and easier to read if the name of the indeterminate do not appear at each occurrence of the polynomial. Definition. A polynomial in a single indeterminate can be written in the form where are numbers, or more generally elements of a ring, and is a symbol which is called an indeterminate or, for historical reasons, a variable. The symbol does not represent any value, although the usual laws valid for arithmetic operations also apply to it. This can be expressed more concisely by using summation notation. That is, a polynomial can either be zero or can be written as the sum of a finite number of non-zero terms. Each term consists of the product of a number, called the coefficient of the term, and a finite number of indeterminates, raised to non-negative integer powers. The exponent on an indeterminate in a term is called the degree of that indeterminate in that term. The degree of the term is the sum of the degrees of the indeterminates in that term, and the degree of a polynomial is the largest degree of any one term with non-zero coefficient. Because x equals x1, the degree of an indeterminate without a written exponent is 1. A term and a polynomial with no indeterminates are called respectively a constant term and a constant polynomial. The degree of a constant term in of a non-zero constant polynomial is 0. The degree of the zero polynomial is generally treated as not defined. For example, is a term. The coefficient is -5, the indeterminates are x and y, the degree of x is 2, while the degree of y is 1. The degree of the entire term is the sum of the degrees of each indeterminate in it, so in this example the degree is 2 plus 1 equals 3. Forming a sum of several terms produces a polynomial. For example, the following is a polynomial. It consists of 3 terms. The first is degree 2, the second is degree 1, and the third is degree 0. Polynomials of small degree have been given specific names. A polynomial of degree 0 is a constant polynomial or simply a constant. Polynomials of degree 1, 2 or 3 are respectively linear polynomials, quadratic polynomials and cubic polynomials. For higher degrees the specific names are not commonly used, although quartic polynomial and quintic polynomial are sometimes used. The names for the degrees may be applied to the polynomial or to its terms. For example, in x2 plus 2x plus 1 the term 2x is a linear term in a quadratic polynomial. The polynomial 0, which may be considered to have no terms at all, is called the zero polynomial. Unlike other constant polynomials, its degree is not 0. Rather, the degree of the zero polynomial is either left explicitly undefined, or defined as negative. These conventions are useful when defining Euclidean division of polynomials. The zero polynomial is also unique in that it is the only polynomial having an infinite number of roots. In the case of polynomials in more than one indeterminate, a polynomial is called homogeneous of degree n if all its non-zero terms have degree n. The zero polynomial is homogeneous, and, as homogeneous polynomial, its degree is undefined. For example, x3y2 plus 7 by 2y3 minus 3 by 5 is homogeneous of degree 5. For more details, see homogeneous polynomial. The commutative law of addition can be used to rearrange terms into any preferred order. In polynomials with one indeterminate, the terms are usually ordered according to degree, either in descending powers of x, with the term of largest degree first, or in ascending powers of x. The polynomial in the example above is written in descending powers of x. The first term has coefficient 3, indeterminate x, and exponent 2. In the second term, the coefficient is -5. The third term is a constant. Because the degree of a non-zero polynomial is the largest degree of any one term, this polynomial has degree 2. Two terms with the same indeterminates raised to the same powers are called similar terms, or like terms, and they can be combined, using the distributive law, into a single term whose coefficient is the sum of the coefficients of the terms that were combined. It may happen that this makes the coefficient 0. Polynomials can be classified by the number of terms with non-zero coefficients, so that a one-term polynomial is called a monomial, a two-term polynomial is called a binomial, and a three-term polynomial is called a trinomial. The term quadrinomial is occasionally used for a four-term polynomial. A polynomial with two indeterminates is called a bivariate polynomial. These notions refer more to the kind of polynomials one is generally working with than to individual polynomials. For instance, when working with univariate polynomials, one does not exclude constant polynomials. Although strictly speaking constant polynomials do not contain any indeterminates at all, it is possible to further classify multivariate polynomials as bivariate, trivariate, and so on, according to the maximum number of indeterminates allowed. Again, so that the set of objects under consideration be closed under subtraction. A study of trivariate polynomials usually allows bivariate polynomials, and so on. It is common, also, to say simply, polynomials in x, y, and z, listing the indeterminates allowed. The evaluation of a polynomial consists of substituting a numerical value to each indeterminate and carrying out the indicated multiplications and additions. For polynomials in one indeterminate, the evaluation is usually more efficient using Horner's method. Arithmetic of polynomials. Polynomials can be added using the associative law of addition, possibly followed by reordering and combining of like terms. For example, if-then, which can be simplified to work out the product of two polynomials into a sum of terms. The distributive law is repeatedly applied, which results in each term of one polynomial being multiplied by every term of the other. For example, if-then, which can be simplified to polynomial evaluation, can be used to compute the remainder of polynomial division by a polynomial of degree 1. Because the remainder of the division of f by is f, see the polynomial remainder theorem. This is more efficient than the usual algorithm of division when the quotient is not needed. A sum of polynomials is a polynomial. A product of polynomials is a polynomial. A composition of two polynomials is a polynomial, which is obtained by substituting a variable of the first polynomial by the second polynomial. The derivative of the polynomial a(n) xn plus n minus 1 xn minus 1 plus a2x2 plus a1x plus a0 is the polynomial nx minus 1 plus n minus 1 xn minus 2 plus 2a2x plus a1. If the set of the coefficients does not contain the integers, then c should be interpreted as the sum of ac with itself, k times. For example, over the integers modulo p, the derivative of the polynomial xp plus 1 is the polynomial 0. A primitive integral or antiderivative of the polynomial a(n) xn plus n minus 1 xn minus 1 plus a2x2 plus a1x plus a0 is the polynomial a(n) xn plus 1 plus n minus 1 xn, n plus a 2x 3/3 plus a 1x 2/2 plus a 0x plus c, where c is an arbitrary constant. For instance, the antiderivatives of x2 plus 1 have the form 1/3 x3 plus x plus c. As for the integers, two kinds of divisions are considered for the polynomials. The Euclidean division of polynomials that generalizes the Euclidean division of the integers. It results in two polynomials, a quotient and a remainder that are characterized by the following property of the polynomials. Given two polynomials A and B such that B0, there exists a unique pair of polynomials, Q, the quotient, and R, the remainder, such that A equals BQ plus R in degree less than degree. By hand as well as with a computer, this division can be computed by the polynomial long division algorithm. All polynomials with coefficients in a unique factorization domain also have a factored form in which the polynomial is written as a product of irreducible polynomials and a constant. This factored form is unique up to the order of the factors and the multiplication by an invertible constant. In the case of the field of complex numbers, the irreducible factors are linear. Over the real numbers, they have the degree either 1 or 2. Over the integers and the rational numbers, the irreducible factors may have any degree. For example, the factored form of is over the integers and the reals and over the complex numbers. The computation of the factored form, called factorization, is, in general, too difficult to be done by handwritten computation. However, efficient polynomial factorization algorithms are available in most computer algebra systems. A formal quotient of polynomials, that is, an algebraic fraction wherein the numerator and denominator are polynomials, is called a rational expression, or rational fraction, and is not, in general, a polynomial. Division of a polynomial by a number, however, yields another polynomial. For example, by 3/12 is considered a valid term in a polynomial, because it is equivalent to x3 and 1/12 is just a constant. When this expression is used as a term, its coefficient is therefore 1/12. For similar reasons, if complex coefficients are allowed, one may have a single term like x3, even though it looks like it should be expanded to two terms. The complex number 2 plus 3i is one complex number, and is the coefficient of that term. The expression 1 is not a polynomial because it includes division by a non-constant polynomial. The expression x is not a polynomial because it contains an indeterminate used as exponent, because subtraction can be replaced by addition of the opposite quantity, and because positive integer exponents can be replaced by repeated multiplication. All polynomials can be constructed from constants and indeterminates using only addition and multiplication. Polynomial functions. A polynomial function is a function that can be defined by evaluating a polynomial. A function f of one argument is called a polynomial function if it satisfies for all arguments x, where n is a non-negative integer and a0, a1, a2, and a constant coefficients. For example, the function f taking real numbers to real numbers, defined by as a polynomial function of one variable. Polynomial functions of multiple variables can also be defined using polynomials in multiple indeterminates, as in an example is also the function which, although it doesn't look like a polynomial, is a polynomial function on because for every from it is true that. Polynomial functions are a class of functions having many important properties. They are all continuous, smooth, entire, computable, etc. Graphs of polynomial functions. Polynomial of degree 2. F equals x2 minus x minus 2 equals. Polynomial of degree 3. F equals by 3/4 plus 3x 2/4 minus 3x 2 minus 2 equals 1/4. Polynomial of degree 4. F equals 1/14 plus 0.5. Polynomial of degree 5. F equals 1/20 plus 2. Polynomial of degree 6. F equals 1/100th. Polynomial of degree 7. F equals. A polynomial function in one real variable can be represented by a graph. The graph of the zero polynomial, f equals 0, is the x-axis. The graph of a degree 0 polynomial, f equals a0, where a0, 0, is a horizontal line with y-intercept a0. The graph of a degree 1 polynomial, f equals a0 plus a1x, where a1, 0, is an oblique line with y-intercept a0 and slope a1. The graph of a degree 2 polynomial, f equals a0 plus a1x plus a2x2, where a2, 0, is a parabola. The graph of a degree 3 polynomial, f equals a0 plus a1x plus a2x2 plus a3x3, where a3, 0, is a cubic curve. The graph of any polynomial with degree 2 or greater, f equals a0 plus a1x plus a2x2 plus anxn, where n0 and n2 is a continuous nonlinear curve. The graph of a non-constant polynomial always tends to infinity when the variable increases indefinitely. Polynomial graphs are analyzed in calculus using intercepts, slopes, concavity, and end behavior.